The go. Okay, good afternoon and welcome to the EM winter course. Today, I just want to go over a couple more housekeeping things. There are a lot of online content resources beyond just this course. And if you are on Twitter or you're on the 3D EM lists, what you'll notice is that there are many EM lectures coming out right now. And that's wonderful because it really shows how well this technology is kicking off. So if you want more information on EM resources online, you can just let us know and we can point you to them. Something that we are fighting in lab right now is also because of the growth of EM, we get so many papers that are EM related. And so this journal club is not meant to be comprehensive in the sense that it's the latest and greatest out in the field. The journal club that we're going to be starting this Wednesday will be more on papers of note that has really changed the field of cryo-EM within the past few years. And some of these papers are well written, some of these are not so well written, and that's the point. They're very good talking points to understand more about cryo-EM. So everyone's welcome to our journal clubs, and they'll start off this Wednesday at 3:30. And Micah is going to be leading those discussions. Okay, so let's get into today's topic. Today, we are wrapping up our EM crystallography section. Our guest lecturer of the day is Hernando Sosa from Albert Einstein College of Medicine. He has done quite a bit in cryo-EM and used helical reconstruction in his research. Something that is quite amazing is that he has more than a dozen, I would say a dozen and a half structures of one particular energy cycle. And that's just amazing tour de force of showing how you can really uncover mechanism. It also shows how some fields are so mature that you need quite a wealth of information to create and understand more of that field. So let's introduce Hernando a little bit more. So Hernando, welcome. How did you first get into cryo-EM?
Well, I, as a postdoc, I always been interested in motor proteins and cytoskeleton. And I did a lot of biophysics as a graduate student, and I used to work with Hugh Huxley, like probably people know by the muscle physiology. And I started doing some EM there, mostly section and classical EM. And at the same time, I was looking at papers on, trying to get the structure of any of these cytoskeletal proteins was like the holy grail to try to understand at the atomic level how these molecular machines work. And then I got the opportunity to work with Ron Milligan, that at the time were having the first very high resolution cryo-EM structure of active. Well, high resolution at the time, we're talking about 20 Armstrong resolution, but that was state of the art at that moment. So he got an opportunity to work with him and on the kinesin microtubule system. And I've been working on this system since that time. I've been switching techniques. When I was in diplopology, I moved to other single molecule fluorescent techniques also to get the structural information. But now with a revolution in resolution, a lot of the questions that we had on molecular structures can be addressed directly using cryo-EM. So it's a very exciting time to actually doing cryo-EM.
So Hernando, what was your first microscope? And follow on to that, what is your favorite microscope?
Well, I don't know it would be the favorite. Certainly the first microscope that I used was a Philips, and it was Philips brand, okay, and that was a microscope that was in Brandeis. Brandeis University was very one of the pioneers in structural biology. But this was not one of the best microscopes there. There was something that was kind of half broken in the lab. And, I got my first experience with that. Then we had other Philips microscope there. They had a 300, there is a 100, there was a 300 that was state of the art. And then in Ron's lab, there was a CM series still of Philips before it became Technite and before it became FEI. So we have been working with Philips Technite. I've been working Philips Technite microscope all the time. And some GOL, when the New York Structural Biology Center used to have GOLs. And
so
what is my favorite microscope? I don't know what is really my favorite microscope. I have a lot of complaints about every microscope, and some of the complaints. So certainly a Krios will be I love the fact that you can use a cassette, the stability, the resolution. That will be the best microscope. Of course, if you consider the price tag, then that would be a big complaint. So.
Well, how do you feel the field has changed over the years? Are there more complaints now? Or are there better complaints or fewer complaints?
Well, the way that I see it, the limitation now is money. Because if you have access to a microscope, you can really, 4 years ago, we couldn't even dream to do what we are doing right now with Cryo-EM. And my dream would be, and it's not just my idea, that a microscope will be some sort of a lab equipment like a spectrophotometer or something like that, because Cryo-EM really has made possible, like if you have a good prep biochemically, there is nothing to stop you to have the structure and in very close to physiological condition. That was just not, that's something that you wouldn't even think 4 years ago. And but the limitation is, microscope time and the cost of the instruments right now.
As Cryo-EM gets larger and larger, are there any fields that are entering the Cryo-EM space that has surprised you?
I don't know if it surprised me, but for example, the channel physiology, the biophysics has been completely taken over by Cryo-EM. All the structure of membrane proteins are being solved now by Cryo-EM and given all sorts of insight about channels, pumps, and so on. So there is, I would say, I don't know, 10 years ago, most electrophysiologists were hard biophysics doing patch clamp and techniques. All of these labs now somehow are doing Cryo-EM.
So then I'll continue.
Yeah. No, in my own field, we work in cytoskeletal protein. EM has always been part of it because these are big macromolecular complexes. And so what is different now is, jumping from the blobology time to the current time is really, we really now can get to atomic mechanism and try to explain mechanical behavior of these proteins almost from first principles just by looking at the atomic structure. That was, that is a big change.
Something that you remember is we used to use film. Right now, the data requirements have greatly expanded. How has archiving data changed for you? Because you can't just store film in a box in your drawer anymore.
Yeah, no, that's that's something that is also amazing because I remember when we used to work in Ron's lab, that was film. So we have 50 negatives there. And there were two things that happened there. So every time that you change the camera, there was a big chance that you will screw up the vacuum of the microscope, and that was the end of the session. So most of the time, your sessions were limited to 50 pictures, and that was it. And worst of that, you didn't even know how good they were as you were taking those pictures. So Now we collect, well, in a couple of days, maybe 4,000 pictures, and you can correct me if I'm wrong, but Matthew that collect the data. So that completely changed how we do experiment. We can look for conformational changes within the data, different conformations, um, improve the resolution because you have a much bigger data set to narrow and throw away images that are not as good for any particular uh, um, criteria. And in terms of data storage, well, now instead of carrying a whole bunch of film, we can carry hard drives. So I keep buying 8 terabytes drive just to move data around. And we need a big data server to store terabytes and terabytes of data. Fortunately, the computer has been improving parallel with that. So storage is not that expensive. So you can buy, but yeah, that's the big difference. I mean, we have terabytes and terabytes of data just by one session.
And I'll wrap up with this last question. What do you feel are the new challenges and opportunities in the field of cryo-EM?
So yeah, one is there is still a bit of a little gap in resolution that is getting solved. Um, it's not a challenge, but it's something that we're gonna move in, try to resolve different conformations in the sample, and so that's one. So there is also another challenge in the part of tomography, improve the resolution that you can get from particles right in situ, in cells, how to get good sections so you can access those structures in a very thin specimen. That certainly is an area that represents a challenge. And in the single particle, or let's say more in vitro world, I think we should be getting routinely be at 2 angstrom or better very soon in a lot of our specimen, and that will improve imaging condition, but also processing. How do you actually to actually retrieve the data that is actually there in the images?
Okay, I'm going to stop my screen share. And if the students also have any questions, I'm going to start asking Hernando some of the questions you sent over last week. But if you have any additional questions, please use the chat. So Hernando, the first question that was posed, how long does a helical reconstruction experiment take? How much data is required compared to single particle? And do you have to merge data like in 2D crystallography?
Well, nowadays I would say most things are very, very similar to any single particle project. The one thing that is different is because you have a helical specimen, from the get-go, you already have you have a picture with many different orientation of your sample there. So there are two competing advantage and disadvantage here. For one side, if you have a good coverage of single particles in a field, you get a lot of single particles in one go. However, with filaments, you want to have the filament isolated and you don't want them to be one overlapping to each other. You want your filament to be isolated. So you cannot put as many filaments per images as you could single particles in a field of view. So you have to reduce your density on side, but with one or two filaments, you get a lot of single particles that in this case will be every asymmetric unit in your helix there. So I think the two complement, and maybe in the case of the helical, you have the advantage that you get a full set of 100 all the orientations in every single sample. So that you probably not gonna, I mean, you're not gonna face problem of preferential orientation or things like that with your helical specimen.
I guess the first part of the question is how long does a helical reconstruction experiment take?
Okay, yeah.
I'm not sure, does that mean that literally how long does it take to collect data? If the person who asks the question, if we're not hitting it fully, just let us know it in the chat. But continue, Hernando.
Yeah, I will imagine. Well, I don't know. This question could have several interpretations. One thing, if you are thinking about the crystallography kind of, I mean, like in the early days, people used to try to get helical specimens because, I mean, the way to obtain the highest resolution structure was to have some sort of symmetry, correct? So if you have 2D crystal or if you have a helical specimen, you could actually get slightly higher resolution than if you have single particles. And that was the case. So you will try to make things helical, okay? So if you try to make things helical, probably that would have been your limiting factor, the same as trying to get crystal of any sort. You just play with your sample until you get the assembly that you want. So, but nowadays you wouldn't do that. Actually, I would say you wouldn't try. The only reason to go from, and that maybe goes to another question, the only reason to go to helical reconstruction is because your specimen is helical. And your helical specimen is the physiological uh, specimen that you want to see. Of course, for example, I work with cytoskeletal proteins. Cytoskeletal proteins bind to macrotubules or bind to actin. So if you want to see how these proteins bind to these filaments, you're gonna have to use helical reconstruction to do it. And the reason that I say that is because with the development of a single particle nowadays, there is no I mean, the first 3D reconstruction was a helical specimen. And the reason was because it was, the description was very, the mathematical description of that specimen was very well defined. So you could develop methods to actually reconstruct the three-dimensional structure from projections, and also because you have all the orientation in a single image. So those were big advantage. Nowadays, that's not a reason anymore because you could actually sort all your orientation in single particles. So you wouldn't go to a single particle unless that is the physiological relevant structure that you want to see. You may argue that in some cases, for example, for small proteins that are, 50 kilodaltons or 100 kilodaltons, that would be very hard to make by single particle. If they happen to bind regularly to a helical specimen, then that will give you the chance to have a high resolution structure of these small proteins because they bind to a helical assembly. But the question was, how long does it take? Well, assume that you already have your helical specimen. Obtaining data in one, we have obtained 3D reconstruction at below 3 angstrom resolution with data with 1 day of data collection. So, yeah.
How large are your filaments normally, and how many filaments do you need? How many filaments do you collect over that 1 day?
Matthew, can you tell what is the latest on that? I will say several. I mean, we are collecting right now more images that we can possibly use. But before we were collecting like maybe 4,000 images, and I will say about the same number of filament, maybe 4,000. But one thing that I have to say, in our case, for several reasons, not all the filaments are usable. So we use a subset of those. So we need to collect, at least twice or three times as much data that we need, because many filaments we are not gonna use. Okay.
Yeah, and for macrotubule, for instance, we have had reconstruction at 300 swim with just 100 macrotubules. It depends on the data sets, but and typically we use between 500 and 3,000 macrotubules.
Okay, we have a question. Does the microscope have to be set up differently for helical work? I hear that 100 kV may be better for EM. Is there a better match kV for helical reconstruction?
We, it is possible. I don't know if it is, you can see the recent paper from Richard Henderson arguing that you can use 100 kilovolts. I mean, in the old days, when we have a microscope here, I used to use the microscope at 120 all the time because it had much better contrast, okay, than at 200, particularly in film. So that was giving us an advantage. But we are collecting data now at 300 kilovolts. So that is fine. If it is, so yeah, I don't see, right now we don't use anything different that people will use for a single particle. The only difference that we used to have at the beginning is that to fully define the helical symmetry and so on, we need to have a very long filament. So depending on the size of your CCD and so on, you have to adjust the field of view to be able to collect a whole filament or a very long filament in a single image. We have been evolved methods to actually determine the symmetry of our microtubule in shorter and shorter segments. So right now, and Matthew, correct me if I'm wrong, I don't think we use either a field of view or anything else that is differently from what people are using for single particles.
Yeah, absolutely. Some of our filaments are less than 800 nanometers that we use. So indeed, we don't need a wood field of view now.
I mean, at the very old time when we were trying to, when I was trying to develop single particle methods to process the filaments and all the things, I remember I used to have several repeats, helical repeats in one image. Okay, so that was a pain in the neck because I even have to reduce the mag to be able to have a whole filament in one image. Nowadays, we don't need to do that. So the setting of the microscope are very similar what we use than that we will use for single particle microscope.
Okay, moving towards preparation of samples, do proteins that tend to form helical tubes also form 2D crystals easily? Is there a preference to shift from one or the other?
I'm not an expert on 2D crystallization, but I have worked in parallel with, and yes, a lot of things that form 2D, because a helical tube is basically a 2D crystal that closes up into a tube. So yeah, that tends to happen. Yeah, and the two seem to coexist.
We have a couple questions in the chat. There was a question on what biochemical strategies can be used to form filaments, like high or low salt detergents, etc.
As I say before, I don't, I mean, that will depend on the particular filament that you are trying to use. We work on microtubules, so we just use polymerization conditions that favor the polymerization and stabilization of tubulin. I mean, the big advantage of cryo-EM, I will say, is that you can look at your proteins in close to physiological conditions. So you can really forget about crystallization or any condition that you need, because you don't need to. So, I mean, my personal feeling is, if I want to have a structure, I just look at it in the most natural way. And nowadays, you don't need to crystallize it. So I will only look at helical specimens that are, well, if you happen to have a beautiful membrane protein that forms beautiful helical tubes, okay, I will analyze that, but I will not go out of my way to try to produce a filament or something that doesn't produce filament.
How hard is it to get well-ordered helical crystals? Or if it naturally does form the helical array, how hard is it to have a very long persistence length?
Well, filaments that they tend to not be as, I mean, the filament that I would normally work tend not to be as ordered. I mean, depend on the protein that you are working. I could show an example of the typical helical specimen that people have used to test, and it is tobacco mosaic virus. It forms a very nice and rigid helical assembly, and they have determined the structure, I think, in the 2.9 angstrom or so. And I think some, maybe Sorchera has some small proteins, alpha-synuclein, or some pieces of it that form helical assemblies that they have a long-range order. Microtubules, in our case, also form relatively well-ordered structure. One limitation that you may see in the old papers of that use helical reconstruction is when we were using the Fourier vessel method. The method itself assumes that you have a perfect helix all along. So as the helix, I mean, you tend to see some distortion of the helix that will affect your final resolution, because you are blurring the signal. That nowadays, because anybody who uses helical reconstruction use some sort of a helical particle approach, even for this. I mean, taking into account the helical symmetry, but you take pieces of the filament that you're going to analyze. So any distortion of the helix that is not cumulative, because you can correct for that as you process your images. Of course, each segment you are assuming that is perfectly helical, which is never any deviation from that is going to affect your resolution. But the persistent length now with the new method has become less of an issue. We actually, in the lab, we are working and go beyond that and starting to be able to, we haven't published that, but it's something that hopefully soon come out, that we can adjust and correct for the position every single subunit in the helical assembly. So it is now converting this problem to almost a single particle approach, when you can correct every single subunit in your helical assembly. So another question, nowadays with image processing, how good your helix is becoming less of an issue. But of course, the more rigid and the more the structure adjusts to a helical symmetry, the easier it's going to be to process, and you're going to get to higher resolution out of the bat without doing any fancy processing.
Could you talk more about the pitfalls of imposing an incorrect helical symmetry, and do people still use selection rules?
Probably not. Probably not. Not everybody use selection rule. Although the selection rule was has its origin when in the Fourier Bessel reconstruction that I don't think anybody use anymore. But the advantage that I had at some point is that I did use the diffraction pattern and the selection rule, because if you look at the lecture with the selection rule tell you which Bessel orders are for each layer line and so on. So one way to determine the selection rule or the helical symmetry, which are two aspects of the same thing. If you know, every selection rule has a corresponding helical symmetry, which is basically how much it turns every subunit and what is erased, right? So these two parameters, when you have them, there is gonna be a selection rule that tell you in a diffraction pattern what are the Bessel orders of all the layer line. So either way, if you know the selection rule, you know what is the rotation per subunit on the right, and if you know the subunit per right, you know the selection rule. So the two are two aspects of the same thing. So if you don't know anything about your specimen, looking at the diffraction pattern and understanding what the selection rule is, it could help you to see what is the symmetry, the helical symmetry of your specimen. There are other ways to do it that you don't have to do a selection rule. Trial and error is one. And if you know more or less what it should be, you can try several ones until you get one that is correct. If it is a specimen that you know, a microtubule, an actin filament, TMB, you probably, the selection rule or the helical symmetry is already published, so you start from that. And any program is going to adjust at the end because you can have a slight variation from the helical parameters in every single specimen. The problem with selecting a wrong selection rule, and that is sometimes the difference into a slightly different selection rule or a completely wrong one could be very, very small, in the 2% of one of the parameters. So, but let's say that was a big problem in the blobology time. Or if you are at that resolution, you have to be very, very careful, because you don't, nowadays, if you have the wrong selection rule or the wrong helical symmetry, and you reconstruct your structure with the wrong symmetry, you're not going to see secondary structure. It's going to be a mess. And you know, if you cannot pass from seeing densities all over the place to something that really look like secondary structure, you probably have the wrong symmetry. So now when we pass the 8 angstrom or 7 angstrom, you already have a reality check. If your structure should be getting to your images and everything tells you that you should get to near atomic to 5 angstrom, and the structure doesn't look like that, that probably is because you have the wrong symmetry. If you are, when you are in the 10, 20 angstrom, that's where a lot of problems there used to be at the blobology time, that you get the structure and basically you get a blob in the wrong place, so blobs. So it's a discussion, okay, I got the blob here, somebody else got the blob somewhere else. Who is right? Now you have a reality check. Whoever gets that secondary structure is correct, and the other is not.
Screening is always an issue, no matter what modality of EM you're using. Are there ways that you can screen for your filament preps without using a microscope that's useful? Like for example, like in single particle, you do size exclusion, DLS, and mols. Are there particular criteria you can use ahead of getting to a microscope to optimize your sample preparation?
Well, filaments are usually visible in the light microscope one way or another. So even without labeling, I mean, because we used to work on fluorescent microscopy, part of my lab, we used to label tubulin. So one way to check if you have filament is just to check if you have filaments in the light microscope. You could use interference microscopy that you will don't need to label the filament to see if you have filament. Nowadays, everybody has a microscope there. You don't electron microscope, so you don't need a fancy electron microscope just to do a negative staining experiment. And that's actually how we usually screen. We just do a negative staining, and that tell you if we have filament, the quality of the filaments, and many things. So we usually screen all the time by negative staining. And for this, I mean, it's a, you know, almost any lab has a a preparation, a microscope that you could use for that type of screening, electron microscope. But yeah, you could do it in principle with lab, but to do good interference microscope probably need more tweaking than to just do a negative staining experiment and put it into in half an hour of on a conventional electron microscope. You already know a lot more about your prep and if it is suitable or not for going cryo.
This may also be a question for Mathieu, which I failed to introduce. So Mathieu Benoit is a postdoc in Hernando's lab. The question would be, how do you prepare samples on a grid? Are there any considerations that are different from single particle? Perhaps one way of going about it would be just to go over your preparation of making the filaments and plunge freezing.
Oh, yeah, so the preparation I do that with Anna, which is here. So for us, we have our main challenge working with microtubule is to have our binding protein on the microtubule. So to do that, we tend to do the grid preparation in two steps. The first step where we add the microtubule onto the grid or filament, and then we add our protein, mainly the kinesin, on top of the grid again after the first blotting step. To maximize the amount of decoration, as we call it, of the microtubule binding protein on the microtubule itself. And to maximize the binding of the microtubule to the grid, we just do a plasma cleaning, and this has been sufficient. Doing that on gold grids.
Do you have any issues with filaments collapsing or orientation?
Yeah, that's mainly depend on the protein we use. Some protein tends to have more than one binding site to the microtubule, so sometimes the microtubule bundles together. So that's one of the reasons we most of the time we don't prepare them we don't do the mix of filament plus binding protein in solution, because otherwise we end up while we load on the grid having a lot of bundles that are much too thick for analysis. So that's why we do a two-step analysis. But even with that, because still the microtubule are not completely bound before the blotting, we still have some local bundling of the microtubule, and we just exclude that during the filament picking step.
So maybe you should add also, like, it's not unique to filaments, but there is a question also eye thickness. So the ice has to be thin, but not so thin that part of your filament get onto the air-water interface.
Yeah.
And I think you guys can recognize when that happens, because the microtubule just don't look well, because, right?
Yeah, yeah. When we start taking pictures, we look for different thickness of ice, take pictures, and we look at the quality of the microtubules in that thickness. And then once we determine where the microtubules look the best, then we get to ice thickness similar to that one. So that we'll do that when we do the atlas and the whole assessment of the grid, and that we do it with you guys. I mean, whoever is helping us in the microscope.
Yeah, I
On
mean,
average, how thick or what's the diameter of your filaments?
I
Uh,
could, yeah. About typically microtubules are on the 25 nanometer, 30 nanometer, depending, or yeah, kind of. So I
and
would say
80 nanometers thickness looks
yeah,
pretty good.
usually we have a thickness that is such that two macrotubule can cross. This enable us to put multiple macrotubule in one field of view. Um, if it's too thin, then we theoretically we get better signal, but the deformation of the filament is such that we get very bad resolution in reconstruction. And if it's too thick, obviously, like in single particle, we lose high resolution information. And something else is also important in filament compared to single, I mean, some single particle is that the large filament are impacted by anisotropy of resolution. So that's also something that we have to correct. So for some small protein, it is not really a concern, but for large filament, it starts to matter, like for large proteins.
right. Yeah. So that's an important issue because we are working with big particles. I mean, if there is any anisotropy there, it's going to affect the image more than if you have a yeah.
We have a few questions on computation. For example, what types of programs are commonly used and what types of computational infrastructure is required for helical processing?
Yeah, here again, Matthew can add, but I will say that nowadays is the same that you would use for single particle. At the very beginning, you know, we after a few years ago, I would say we need less compute. I mean, because we were not even using a GPU, and we were getting structures, in the less than 400 resolution in a day or so with a multi-core processor. But nowadays, I would say a good workstation with at least two GPU. I mean, the same that you will use for helical particle reconstruction. Yeah, I mean, the size of the data, the 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 need for GPU. I mean, if you are using Relion, for example, that most people are using now, we are using Relion too. You need GPU. Some other programs are better, are optimized for CPU. So I like to have a workstation with which at least have 30 threads or so you can parallelize some. But I would say in general, the same requirements that for a single particle approach.
You talk about Reliant. What are the common packages people use now for helical reconstruction?
I would say people still use whatever they use. And they have used. So we have used during my say tenure doing helical reconstruction almost everything. Okay, so and we use a little bit of everything. Uh, we use even a spider for some early part of the process. Nowadays we could maybe implement everything in Relion because if I will have I have a slide, but the steps in the analysis will be first classify the filaments. I have a all routine to the spider to do that, but certainly you could implement that using a 2D image classification in Relion. There is no need to do it in Spider, but So people now rely on free align. They have interface to use helical symmetry. So those will be the two programs that I use. There is another programs, I don't remember the name, a package that use Carsten Sasche in Germany, but I don't know how commonly it's used. But now everybody is familiar with Relion, so that would be a good technique. At the beginning, we didn't use that much Relion. One advantage that I would say from other programs, like we were using FreeAlign to do a lot of refinement, is that it was very, very quick. So we were getting reconstructions, 3D reconstruction in a question of hours instead of days. And that was helpful to actually troubleshoot and refine a lot of the programs and find, before going into the final refinement, that certainly we find some advantage using Relion. But yes, so we use a combination of programs, and the last refinement we use Relion to do it. You could add something, Matthew, that I haven't said or I forgot to add?
Yeah, no, nothing.
Yeah, I mean, he's doing the processing and he's been optimizing everything. So, yeah.
Overall, validation has gotten more complicated and easier because now if you can see that you have right-handed helices, it's more often known that you have a correct reconstruction. But is there anything that you know that is different about deposition of helical reconstruction or validation than, let's say, single particle?
Well, we are putting more data now. So we do similar to the single particle, divide the data set in two. So we have the two maps, every map that we use to estimate resolution. I mean, all the methods are converging in a way. So everything is very similar to single particle. So we use the FSC criteria to report resolution. One thing about helical specimens, because they are big, I mean, it's very common that the resolution is not constant around the structure. So we usually report an overall resolution that it could be, let's say, 4 angstrom. But the microtubule part is usually a much higher, and that's not only for us. Every time that you see a filament reconstruction, it is probably at the filament at the closer to the axis of the filament is going to be at the highest resolution. And as you go out of the filament, the resolution gets progressively worse. So we report usually resolution, the overall, the microtubule resolution, the kinesin resolution, or also make a map of the local resolution. So that's something that I would say everybody should report when it's a helical specimen, because if you see somebody telling you, oh, this microtubule resolution is a let's say 5 angstrom, well, they probably are talking about kinesin, not the microtubule there. And the kinesin probably is at 9 or maybe even lower. So that's important to keep in mind. And the same with actomyosin. The resolution at the outer part is usually worse than at the center of the axis.
There has been a lot of development in algorithms from Bayesian polishing to variability analysis. How has that helped helical reconstruction?
Well, Matthew, we haven't published that yet, and we are in the process, but certainly that's the next step. I mean, the big disadvantage of helical reconstruction was great. You have a huge helical assembly, easy to find, give you a whole of different orientation. But one thing that we have a disadvantage with pure helical reconstruction is that we cannot say, for example, if one of the asymmetric units is in two conformations. If you have an equilibrium of conformations, you have no way, because you always have a helical average of every single subunit. People have been working in ways to in symmetrical assemblies to start to refine individual subunit, and Matthew has been working on that on the kinesin microtubule. So we hope to get something that in that where we actually, well, we can see actually different conformation in the helical assembly, that by just averaging the whole structure, and that will also allow you to correct for distortions on the helical structure that will also bump the resolution a little bit.
I think there's a couple questions I think you already answered. Why are helical tubes particularly good samples for cryo-EM reconstruction? And is it because that there's a diffraction pattern, you can look at molecules that are smaller than with single particle?
Yeah.
I think you touched upon that already. And then the last question also that I have in my deck would be, Bill in his lecture about 2D crystallography talked about a missing cone. Is there something similar in helical?
Yeah. No, well, actually, there is not. And that is the big advantage of helical crystal as opposed to the crystal. There is no missing cone whatsoever. So because you have a filament, and you know your subunits are all orientation in 180 degrees, you don't have a missing cone.
Okay, well, the last question, and I'll just throw out there, I don't know if you have an answer for, if in helical reconstructions, do you know the rough size or in molecular weight of protein subunits solved by helical versus single particle, and also the resolution ranges versus single particle? It's only natural because I think single particle has been growing in popularity, so people always want something to compare something else with.
Yeah, well, I have here, let's say, I prepare just I just went to the database and look at recent structures solved by okay, let me share the screen. Okay, can you see it?
Yes.
Okay, so these are some structures. I just went to the EM database and ordered the structure that say helical processing. I may have missed a few because the database has a weird way to check, but so that these are a structure that somehow in the procedure say that they have used helical reconstruction, but if they use a single particle helical reconstruction hybrid, they may not have been listed. So these are specimens that are listed have used helical reconstruction some way. So you can see there is TMB at 1.9 angstrom resolution. So the size of each TMB subunit, I don't remember what it is, but it's in the order of 20 kilodalton or so. So that's a very small protein. Okay, we work with kinesin proteins that are in the order motor domain 30 kilodalton. So yes, in a helical specimen, you can work with, if your subunit could be very, very small. I think I have seen maybe a comparable resolution, microtubule binding proteins that probably are in the 20 or 30 kilodaltons. So yes, I will say you can resolve in your helical assemble a single alpha helical. So if you have a protein that is just a, just a little piece that binds regularly to a filament, you probably can solve that structure at 1-2 angstrom resolution. So the limit of size is a lot less per subunit. Of course, we are hitting the size because we are working with a huge macromolecular assembly. But every individual subunit can be very, very small, a lot smaller than the 50 kilo Dalton limit of that you will say on a single particle experiment. Yeah.
Okay, last call for any questions for Hernando. Otherwise, Hernando, do you have any last words on the technique of helical reconstruction?
So yes, in general, what I will say is that, it's an approach that I will use because it's the physiological specimen. Microtubules, here is another example that I mean, there are many examples in biology that there are helical filament. So in those cases, the natural approach to use to determine the structure will be to use, to take advantage and to use helical symmetry to solve your specimen. In terms of methodology, it is converging very much into to the single particle approach, but you need to understand what a helical assembly is in order to take advantage of it and to actually get as much resolution as you have your specimen.
Okay, well, thank you, Hernando, for coming today and talking to us more about helical reconstructions. If you have any further questions, you can always email us and we'll forward those questions to Hernando. And for the class, thank you for coming. And don't forget, anyone who wants to come to Journal Club, you can come this Wednesday, same link, same time. Have a good afternoon.
Okay, well, thank you. Thank you, everybody. Bye.